We usually think of logic in really simple terms, right? It's either true or false, black or white. But what if there's a much more powerful kind of logic out there? One that's actually built for all the gray areas in between. Well, today, we're going to dive into exactly that, the logic of nuance and complexity.
I mean, really think about it for a second. We talk about things being on or off, right or wrong. But is that how the world actually works? I don't think so. From sharing an opinion that's kinda sorta true, to measuring temperature, reality seems to have way more shades than just two.
All right, so here's the best way to think about this. Classical logic, the kind we all learn about, it's like a standard light switch. It's binary. It's either on or it's off. True or false. That's it. But many-valued logic, now that's more like a dimmer dial. It can be all the way on, all the way off, or literally any of the infinite shades of brightness in between. It's a logic that's built for nuance. So what do we call this logic of nuance? Well, it's actually a whole family of formal systems, and they're known as many-valued logics, or MVLs for short. And their entire reason for existing is to do the one thing classical logic just can't: handle the beautiful complexity of the real world. So here's the big idea, the fundamental shift. Instead of just two options, true and false, MVLs open the door to a whole set of possible truth values. This could be something simple, like three values: true, false, and maybe unknown. Or it could be a massive, infinite spectrum, like every single number between 0 and 1. Okay, but wait, this creates a brand new problem, right? If you've got all these different values floating around, how in the world do you actually work with them inside a logical proof? Logicians needed a new tool, a new mechanism, to make this whole system, well, work. Exactly. How do you formally write down that our dimmer dial isn't at 0 or 100, but it's sitting precisely at, say, 65%? You need a clear, totally unambiguous way to label the exact state of any statement you're working with. And the solution they came up with is just brilliant. It's elegant in its simplicity. It's called a signed formula. And it's really just a pair of things. You take your logical statement, which we call a formula, and you directly pair it with one of its specific truth values.
And the way we write this down is just beautiful. It's this simple little bracketed pair. That's the core building block of the whole system. It's just a formal way of saying, hey, this statement, F, has this exact truth value, Ti. It's basically a tag. That's it.
Oh, I love this quote from the source material because it just makes the whole concept click, doesn't it? That signed formula is the photograph. It freezes the dimmer dial in its exact position and tags that picture right onto the statement so you never, ever lose track of its value. So you might be thinking, okay, it's a fancy tag, big deal. But no, this little idea of tagging a formula is so much more than a notational trick. It has these profound consequences that basically unlock the ability to build entire, incredibly powerful logical systems. Let's take a look at what that power really is.
So what does this tag actually let us do? Well, first, it lets us take all those proof systems we already had and adapt them to handle way more than two values. Second, it makes the truth of a statement completely explicit. It's not hiding somewhere. It's right there in the tag. And finally, and this is huge, it forges this incredibly strong link between the symbols you write down, the syntax, and what those symbols actually mean, the semantics.
And here's a great example of just how deep this goes. You see, classical logic has this famous rule called the law of the excluded middle. It says a statement has to be either true or false. There's no middle ground. But signed formulas, they let us build a whole new version of this principle, one that creates a bridge to include all the possible values in between. Of course, once you have a great idea like this, you don't just stop. Logicians saw how powerful the signed formula was, and they started building on top of it, creating even more sophisticated and powerful toolkits for exploring these really complex logical worlds. So the first big upgrade was a really clever question. What if we don't have to assign just one specific value? What if we could tag a formula with a whole set of possible values? You can imagine how this makes the system way more efficient and flexible. And you can see the difference so clearly right here. On the left, we're making a very specific claim. The formula has exactly this one value. But on the right, we're saying something more flexible. It could have value 1, or it could have value 4. This gives us so much more room to maneuver in our proofs. And this ability to work with sets of values just opens the floodgates to entirely new ways of building proofs. Think about it. Instead of a simple two-sided scale, for true and false, you can now build a structure that tracks many, many possible outcomes all at the same time. And that simple idea, signing with sets, just blossoms into this whole advanced toolkit. Now, we don't need to get lost in these names, don't worry. The key insight here is that each of these is just a different, specialized tool designed to build more efficient and more powerful proofs for our complex, dimmer dial world. Okay, this is all really fascinating theory for sure. But so what, right? What's the point? Why does building these abstract logical systems actually matter in the real world, to you and me? Well, it turns out this abstract theory is the engine running under the hood of some very practical, very real technology. While it's absolutely crucial for super technical fields like automated deduction, the biggest impact for most of us is in fuzzy logic and artificial intelligence. This is the logic that helps your washing machine figure out just how dirty your clothes are. Fuzzy logic is basically our dimmer dial in action. Truth isn't just on or off, it's any value between 0 and 1. So a statement like, the water is hot, can be, say, 0.8 true. This is absolutely essential for AI that has to operate in the messy real world. A self-driving car, for instance, doesn't just see obstacle or no obstacle. No, it calculates degrees of risk, which is what allows it to navigate a complex, uncertain environment. So let's just quickly recap our journey here. We started by realizing that the real world isn't a simple light switch, it's a dimmer dial. We learned that many valued logics were built specifically to handle that nuance. The key invention that makes it all possible is the signed formula, that simple but incredibly powerful tag. And finally, we saw how this abstract theory has a direct line to powering real-world technologies that we all use every single day. And that really leaves us with one last thought. This entire field of study grew from challenging the simple binary of true and false. So the real question for us is, what other big problems in technology, in society, maybe even in our own lives, could we start to solve if we just got a little bit better at thinking beyond a simple yes or no?